application of cryogenic liquids. Cryogenic liquids are used in a wide range of applications. Household fuels such as liquefied petroleum gas, LPG, and liquefied natural gas, LNG, are frequently used. These liquids are kept in enormous storage tanks. This type of tanks. Through pipelines, gasified LNG is transported to every home for fuel. Large liquid oxygen containers are installed in hospitals. They also give the patient gasified oxygen. In the liquid phase, we can store much more gas molecules than we can in the pressurized gas phase. It is far more cost-effective to store the liquefied gas and then evaporate it when it needed. The rocket propulsion system uses liquid oxygen as an oxidizer and liquid hydrogen as fuel. The hydrogen bubble chamber, which is filled with liquid hydrogen, detects the high energy particles produced by the large particle accelerator. Blood, fertilized eggs, bone marrow, and the human or animal semen are all preserved for a long time in liquid nitrogen cooled containers. Fertilized eggs must be stored for a long time before being inserted in the womb for artificial insemination. For animals in danger of extinction, the semen or fertilized egg must be kept for an extended period of time. Liquid nitrogen-cooled containers are utilized for this purpose. Cryogenic surgery is a procedure used to treat Parkinson's disease and other types of resins. Food is frozen instantly on a conveyor belt passing through the liquid nitrogen bath or gaseous nitrogen called the tunnel. In this instance, all liquid nitrogen exposed food surfaces are immediately frozen. As a result, the flavor and aroma are properly preserved. The cryogenic freezing technology also takes less time to freeze food than the traditional freezing approach. Wires of niobium titanium alloy are used to make the superconducting magnet in MRI scanners. Below 9 Kelvin, this wire becomes superconducting. As a result, liquid helium is required to keep the superconducting wires cool. A superconducting magnet is also used to levitate high-speed trains traveling at 500 km per hour. This slide shows the container cooled with liquid nitrogen. We can keep fertilized eggs or semens in this container. This table shows the boiling points of cryogenic liquids at atmospheric pressure. So helium has lowest boiling point, 4.2 Kelvin, hydrogen 20 Kelvin, neon 27 Kelvin, so other liquefied gases have boiling points given here. This figure shows the magnetic levitation phenomena, and this is magnetic levitation train. Basically, any gas can be liquefied if it is in a gaseous state at room temperature. A storage door with highest thermal insulation should be used to keep the liquefied gas with a very low boiling point. Liquid helium has the lowest boiling point among cryogenic liquids, just 4.2 Kelvin at the atmospheric pressure. To keep liquid helium secure, we will need a super insulated door with excellent thermal insulation. So this figure shows transportable containers for liquid helium, this one, and liquid nitrogen. Now let's see the liquid helium. Only around 0.0013% of the air is made up of helium gas, and only 10 to the minus 5% of that is made up of helium-3 gas. So helium-3 gas is very rare. The remainder is made up of helium-4 gas. Since there isn't enough helium in the air, helium gas is extracted from natural gas, which has more helium in it. Helium gas is produced in the nuclear reactor by carrying out nuclear reactions, this kind of nuclear reactions. So you can produce helium-4 and helium-3. The previously described reactions occurred in the natural gas, increasing the amount of helium content. 2 protons and 1 neutron make up the nucleus of helium-3 atom, result in a fermion with a nuclear spin of 1/2. On the other hand, helium-4 atom's nucleus has additional neutron, making it a boson with a nuclear spin 0. So helium-3 atom is fermion, and its nuclear spin 1/2. On the other hand, helium-4 atom is the boson, and with nuclear spin 0. Even at absolute 0, helium is still in a liquid phase. If the temperature is decreased, all gases first transition to liquid state and then solid state. So that is the typical solid liquid gas phase diagram. So all gases first transition to liquid state if we lower the temperature. Then after that, if we lower the temperature more, then it will become solid. So all gases follow this kind of transition. However, liquid helium does not solidify even at absolute 0. Here we can see the phase diagram of the helium-4 and the helium-3. So you can see here liquid helium does not solidify even at absolute 0, still liquid. Okay. We needed to use a lot of pressure to push the helium atoms together tightly enough to form solid helium. So you have to apply very high pressure to make the solid helium. Compared to helium-3 liquid, which requires a pressure of 34 atm. So we need the high pressure of 34 atm to solidify the helium-3 liquid. On the other hand, for helium-4 liquid requires a pressure of 25 atm at absolute zero to solidify. So here you can see here we have to apply more than 25 atm, then the liquid helium becomes solid helium. Okay, it's also 34 atm, then liquid becomes solid. Okay. And also we'll discuss shortly the next slide. Liquid helium has two phases. One is normal liquid and the other is a superfluid. The same in the helium-3 liquid. It's a normal liquid and superfluid. Okay. Due to its inert nature, helium doesn't have dipole moment. Therefore, there is little van der Waals force between neutral helium atoms. Also, because of its low mass, the helium atom has a very high quantum mechanical zero-point energy. Zero-point energy is given by this equation, and zero-point energy is inversely proportional to mass. So helium has very small mass, so it has very large quantum mechanical zero-point energy. As a result, the van der Waals force, attractive force, is insufficient for overcoming atoms fluctuation resulted by the quantum mechanical zero-point energy. In order to overcome the quantum mechanical disturbances and solidify, external force, high pressure, is required. This table shows the people who received Nobel Prize for liquid helium. 1913, Owens received the Nobel Prize for physics. He actually produced liquid helium first. So contribution as production of liquid helium-4. In 1937, Kapitsa received also a Nobel Prize in physics. His contribution is the discovery of short fluidity of liquid helium-4. Yeah. In 1962, Landau received the Nobel Prize for the theory of phase transition for liquid helium. 1996, David Lee, Richardson, and Osharov received the Nobel Prize in physics for their discovery of short fluidity of helium-3. And 2003, Alexei Abrikosov and Ginsburg received the Nobel Prize in Physics for their theory of the superconductor and the superfluidity. Now let's see the superfluid. Below a specific temperature, liquid helium exhibits superfluid characteristics, which have infinite thermal conductivity and no viscosity. There are no other fluids in which these phenomena can be seen. The superfluidity can be only observed in liquid helium. Once discovered this superfluidity in helium-4 liquid in 1920. Both Einstein and condensation explains this superfluid behavior. However, the precise theoretical explanation has not yet been given. The helium-3 liquid wasn't expected to be superfluid because the helium-3 atom is fermion and could not exhibit the Bose-Einstein condensation as in helium-4. However, superfluidity in helium-3 liquid at 2.5 millikelvin was discovered in 1972 by Oserov et al. The Cooper pair model for low temperature superconductivity provided an explanation for this phenomena. The van der Waals forces, spin fluctuation force, exchange interaction, as in ferromagnetic material, and other forces combine to form co-pairs or bosons in the helium-3 liquid. So you can see here helium-4 is normal fluid here in this region. We call helium-1 as normal fluid, and in this region liquid helium become superfluid, so we call helium-2. In helium-3, normal helium-3 in this region, and there are several reasons for superfluid in liquid helium-3. So we here helium-3 and A, so different phase. This data is the specific heat as function of temperature. Superfluidity of liquid helium-4 occurs at 2.176 Kelvin at 1 atm. The abrupt change in specific heat is the indication of this superfluid transition. So this is called lambda point. The specific heat near the transition resembles the Greek letter lambda in shape. So the lambda transition is the name we give to this superfluid transition. We can also see this kind of the abrupt change in specific heat for helium-3. So liquid helium-3 has the same abrupt change in the specific heat at the superfluid transition temperature, that is 2.5 millikelvin. Let's see the change of the superfluid transition temperature as function of pressure. So this gives the detailed phase diagram near the superfluid transition. As pressure rises, so in this direction, The superheat transition temperature decreases. You can see follow this line. So if as the pressure rises, the superheat transition temperature decreases. The triple point of solid liquid helium 1 and 2 has been found to have the lowest transition temperature, which is 1.76 Kelvin. So at this point, this triple point, also liquid helium 1 and liquid helium 2 phase and solid helium. So three phases meet. So there's a triple point. So at the triple point, the super transition is lowest. That's 1.76 Kelvin. This slide shows the what kind of phenomena can be obtained in the superheat liquid helium. In this figure, even if the vessel only touches the superheat surface, so this is more than touch, but if the containers just touch the surface of liquid helium, the superfluid. So even if the vessel only touches the superfluid surface, the fluid will still climb up the surface. So fluid climb up, right, and fill the vessel. Is also the same behavior can be obtained if we just touch the surface of a fluid. Then we can see inside the vessel fluid is filled. So even if the vessel only touches the superfluid surface, the fluid will still climb up the surface and fill the vessel. The zero viscosity of superfluid is what causes this to happen. So there's no viscosity in superfluid, so the superfluid can climb up the surface of wall of the container and fill the container with superfluid. The superfluid filled vessel, this superfluid filled vessel, is lifted above the fluid surface. The fluid then ascends the vessel surface and empties it. So superfluid climb up the wall of container and empties the vessel. So this shows this picture shows this behavior. Now let's see the two fluid model. The fluid exhibits no viscosity when we pass the superfluid helium through a narrow channel of the pipe. So no viscosity. However, if we examine the viscosity of superfluid with a viscometer spinning in the fluid, we find that it is identical to that of normal fluid. So if we use a viscometer, then we observed that superfluid has the same viscosity as normal fluid. The two fluid model emerged to reconcile these two paradoxical experiments. The liquid helium in the superfluid state, according to this model, two-fluid model, is made up of two fluids, namely superfluid and normal fluid parts. As the temperature drops, the percentage of the superfluid components rises. The region of the two fluids cannot be differentiated even if the fluid is made up of both superfluid and normal fluid parts. Only the superfluid part of the fluid could pass through the narrow neck in the experiment, demonstrating zero viscosity behavior. So this superfluid passes through the narrow channel. Superfluid shows the no viscosity. That the experiment. Because two-fluid model, superfluid consists of normal fluid part and superfluid part. So in this narrow channel experiment, only a superfluid part has no viscosity and pass through the channel, so we can observe that the superfluid has no viscosity. On the other hand, in the viscometer experiment, only a part of normal fluid stuck to the viscometer surface, showing the normal fluid's viscosity. So, using this two-fluid model, we can explain these two paradoxical experimental results. This two-fluid model was proven by this torsional oscillator experiments. So that is the schematic figure for these experiments, torsional oscillator experiments. The torsion rod is immersed in the liquid, and we oscillate this torsional rod, and then normal part stuck to the surface of the torsion oscillator, and we can observe the period change of the oscillator. So by observing the period change of this oscillator, we can deduce the normal part of the fluid. So you can see here below the superfluid transition. At this moment, lambda point above lambda point, right? All fluid is normal fluid. But if we reduce temperature below lambda point, then superfluid part increases. So this way. So superfluid part increases. On the same time, the normal fluid part is decreasing. So at this temperature range, there's no normal fluid part, and all fluid becomes superfluid. So at this region, normal fluid and the fluid coexist. So using this torsional oscillator experiment, two fluid model was experimentally proved. So this torsional oscillator experiment was proposed by Androni Kashvili. So he proved this two-fluid model experimentally. So the two-fluid model was proven by the torsional oscillator experiment. This figure shows the there's a silicon cell. Inside silicon cell, the fluid is green. So using torsional oscillator experiment, we can observe the shock fluid density as function of temperature. But in this experiment, shock fluid density measurements for the confined helium between two silicon wafers using a torsional oscillator experiment, and the results presented in the Journal of Physical Review Letters in 1989.